I figured it out right here at the top. I'm not sure if you guys watched the video, but it was in presenter mode. Anyway. All right, so scientific notation is basically the exponential notation. This is essentially a really convenient way for scientists or anybody in general really to express numbers in really large numbers or really small numbers in a concise manner. I'm hoping you guys remember how to do this. I think I'll go ahead and work through a few practice problems here later today. But the main thing is that you're going to be moving the decimal such that it is only one digit to the left of, or only one non-zero to the left of the decimal, and then everything else is after that. And then you have times the multiplier times 10 to whatever, and that whatever number, the exponent is how far you move the decimal to get to that. One of the cool things about scientific notation and why it's really useful for this class in particular is that remember everything in front, all those digits are significant. So if you're ever having any issues with conveying scientific notation due to like zeros and whatnot, you could always just go ahead and put it into scientific notation, and then it'll be correct. All right, we talked briefly about density last time. This is, was this intensive or extensive? It's an intensive. So for example, if you have, say, a drop of water versus a gallon of water, they all have the same, the drop and the gallon have the same density because it's going to kind of scale to each other, right? The more mass you have, the more volume you have. So it doesn't matter how much you have. After just the ratio of them, it'll be a constant value, and that means that it's intensive, does not depend on the amount. So we have this example here. It says, calculate the density of an object that has a mass of 197 grams and a volume of 10.2. All right, and then I have this other question here that I want to work through as well, and showing you how we can use density as a conversion factor. All right, one sec to get pencils and pens. We're writing stuff today. All right. Got green, red, blue, purple. All right. Speaking of phones, I'm going to use the calculator on my phone. So I do use my phone for a calculator in this class, and the main reason why is because I can put it onto the document camera and it's backlit. If you're going to be following along with me, I recommend that you actually get your scientific calculator and like pretend like you get used to it if you're not really all that familiar with it. Just that way, if you're not learning it for the first time while you're taking the test, right? Right, let me switch over to camera. Right. All right, so here we have density is equal to mass over volume. So this particular question, it said 197 grams was our mass, and then we're given the volume. So in this case, we're just going to go ahead and plug into it. So it's 197 grams over, and the volume was 10.20 centimeter cubed. Are we able to estimate about what that value is going to be without punching any numbers in? Should be about 19 or 20 or so. So 197 divided by 10.2 is 19.3. How many six should I have in my answer? 3. And the reason why is because we're following the multiplication and division rule, which states that we go by the least significant, or the one with the least number of significant figures. So to 3 sig figs, it's 19.3, and what are my units?
Grams per centimeter cubed.
Yep, grams per centimeter cubed. So it's always a mass over a volume. Go ahead.
For the bottom, how many significant figures are there? 10.20.
I'm seeing 4.
4.
Yep. Yeah, that trailing 0, because it's to the right of the decimal, is significant.
Okay.
All right, the next question asks about some gasoline. So you have some gasoline that has, so this is the next problem, a mass of 60.0 kilograms. And we also know that the density for gasoline is about 0.7. This little page here is giving 0.752. And the units are grams per centimeter cubed. All right, we didn't quite go over unit conversions yet, but I think we're going to have to use something here. And the reason why is because the units don't match, do they? So we have a kilogram on the mass unit, and then we have gram on the density term. And once again, here the question is asking us for volume. So one way you could approach this is to go ahead and take the original equation and solve for V. So D is equal to M over V. Solve this for V, and I believe it looks like it's what? Mass over density. And then plug your numbers in. What I would like for you guys to at least try would be to use this density unit as a conversion factor. And that is a great way we can go between volumes and masses, right? So what I'm going to go ahead and do is you can actually shorthand some of the conversions here by recognizing that kilogram and gram. So remember how many kilograms, or sorry, how many grams are in a kilogram? It's 1,000, right? So instead of the kilo, you can just write times 10 to the 3 there instead. So this is technically not scientific notation. It's just saving you a step in your conversion. So 60 times 10 to the 3 in place of the kilo symbol, grams. And then if I'm treating this as a conversion factor, you basically want the given unit on the bottom so it cancels, and the desired unit on the top so it remains. So in short, we want grams on the bottom, we want the volume to remain. So then we can plug in our density unit there. So that 0.752, notice how we have the gram unit on top. So that 0.752 goes with wherever gram went. So grams on the bottom, so that's where the number goes. And you have to remember what number I put on the top? It's 1. Yeah, so the way we would read this out, if you were to just read it out of the sentence, it says that there's 0.752 grams per 1 centimeter cubed. Okay, so you can set it up as a conversion factor. So in the case where you had to then, I don't know, convert this to gallons or something, you can have like a long string of calculations going here. Either way is fine, but you may notice here, if you compare it to the original setup, I am technically doing the exact same thing, right? I am taking mass divided in by density. All right, so then we have 60 times 10 to the 3. That was your kilogram term, and then go ahead and divide that by 0.752. And I'm getting that number there, the 79, et cetera, et cetera. How many sig figs should my answer have? 3. All right, so to 3 sig figs, I'm going to report this as 7.98 times 10, looks like 10 to the 4. And my units are centimeter cubed, like so. How many sig figs are in that number? Infinite, yes, you guys are getting it. Yeah, anytime you have any kind of conversion factor, table information, those kind of values are considered to have an infinite number of significant figures. All right. Switch back over to this. I have to go switch it back in the recorder. All right, temperature conversions. So you guys are going to have to know how to go back and forth between the different temperature scales. You know, Fahrenheit, Celsius, and Kelvin. You know, since we live in the U.S., we have to work in Fahrenheit. The thing about this scale that I think is interesting, or that you guys should be aware of, is that anytime you have any kind of scale, there's typically a reference point. And water is often used as a reference for many different scales throughout science. For example, here we have the 0 mark is the freezing point of water. And we also have the centimeter cube term with volume in grams. So the definition there is 1 gram of water is exactly 1 centimeter cubed if it's pure water. So once again, we're using water as a reference. And you guys will see this as we go along through science, or in your science courses, that water is often a reference point. All right, so a few things about this is I would like for you guys to, one, know the equation to go between them, but I want you guys to physically understand why we're using this equation. I'm not a big fan of people just knowing equations and not knowing what the equation is actually saying to you. That's actually a big thing about understanding science, is understanding what the equations are saying. So in the Celsius scale, it was defined to be 0 to be the exact point where water freezes, and then 100 is where water boils. I'm not quite sure where the Fahrenheit came from, but there are some correlations here. So it turns out that 32 is where temperature freezes. Sorry, where water freezes. So when people say that it's below freezing outside, people are basically saying that it's below 32 Fahrenheit, not below 0. Below 0 and below freezing are completely different. I'm not sure if you guys have been in below 0 weather. It is awful. It's definitely much colder than if it's like this 30 degrees out. It actually feels warm. Interesting thing about that is my first time coming to Montana in the winter, people were still wearing like shorts and like tank tops in like October, and it was below freezing, literally below freezing outside. People are still running around that way. And then I realized that after you've gone through one of their crazy winters where it does get below 0 all the time, and it gets above freezing just a little bit, it feels warm outside. So then I was running around and flip-flops when it's just 30 degrees outside. Not anymore, but yeah, during grad school it felt that way. It felt warm. Excuse me. So the one thing we have here is the offset. So we have 0 degrees C for the freezing point, and then we have 32 F for the freezing point in Fahrenheit. We have to account for that offset. That's why you have that plus 32 term in the temperature conversion. The other thing that we account for is the difference in how fast the scales climb. So you go from 0 to 100 versus 32 to 212. And what is that difference? Is that 180? So if you have 180 versus 100, that's essentially 9 to 5. And that's where that 9 to 5 factor comes from, or that 1.8. It's basically, that's accounting for how fast the rates climb, and then we have the offset. So that's where these equations come from. They're in here. There we go. So here are your equations. So for going from Fahrenheit, Celsius to Fahrenheit, we're going to use this one. So you're given Celsius, what is Fahrenheit? The way I remember this is that if you're going to a Fahrenheit, typically Fahrenheit numbers are larger than Celsius numbers. So that's the one where we put the 9 on top. And then in the case where we're going from Fahrenheit to degree C, typically degree C is lower. And then we put 5 on top instead, the lower number. I think it would be useful for you guys just to, as you go along in your labs, to get kind of a physical sense of how hot and cold Celsius is, just because you're going to be working with Celsius pretty much all throughout your scientific career. You don't use Fahrenheit really all that much. But you probably will be in your everyday speech, because even as a chemist for a couple years now, I still use Fahrenheit saying that it's 100 degrees outside.
Did you say you want us to memorize these and be able to use them?
You should. These are things that I think you should memorize. I do provide equations, though, for you guys. Yeah. But I think if you actually just know it and practice it, then it's probably better. Another thing here is looking at the Celsius to Kelvin. The only thing you're accounting for here is the offset. So if you look at the scales here, going back the slide back, the scales change exactly by 100 on both the the Celsius and Kelvin scale, and the freezing point and boiling point of water differ by 100 degrees. So we're only accounting for offset. We're not accounting for different rates of change. So that's why you don't have a ratio term inside of the Kelvin to Celsius. We only have like the equivalent of the 32. So it's just at 273.15. Go ahead.
On the Celsius to Fahrenheit equation, should the 32 be in the parentheses? Because it's out on the other.
Yeah, so here, so the main thing you need to do is account for offset depending on the direction. So in this case, you account for the offset after this multiplication. If you're going from Fahrenheit to Celsius, you subtract the offset first.
Okay, thank you.
Yeah. And then if you know one of them, you can't algebraically get to the other one. But I'm glad you brought that up, though, because your order of operations here matter. So make sure that you use your order of operations there. You got a few conversions here. So if I were in, say, the UK where they use the metric system, and I said, oh, it's 30 degrees outside, and would that tell you if it was hot or cold outside? And suppose they were talking in Celsius. It's 30 degrees hot or cold outside. It's pretty nice out, or pretty warm depending on who you're talking to. It's not time for your jackets yet. All right, but I want to go ahead and do a little bit of practice here. We do have a few practice problems here to work with that we'll go ahead and do. Oop. We have this one here, 101.5. That sounds about what it's going to be here today, doesn't it? I think it's going to be about 100 degrees today. All right, so DocCam. And then this thing, we just switch over to DocCam. All right, and once again, that value was 101.5 degree F. And just for the sake that we're getting practice, I want to go ahead and convert this all the way to Kelvin. But before we can do that, we have to go to degree C first. So since we're going to Celsius, that's the smaller unit, you want to use the equation that has the 5 on top. So degree C is equal to, and if you're actually worried about how the units work out, this 5 over 9 technically have units attached to them. So it's actually 5 degrees C per 9 degree F. I know they're typically dropped. This is probably the only time this semester I'm going to write them in, but they're typically dropped out. And then right here we have 101.5 degree F. You may notice now that the F's would cancel and leaving us in degree C. And this one, do I have the 32 on the inside or the outside of the parentheses? Inside. So that means if I'm following the order of operations, I need to apply that rule first. And I did mention to you guys last time when we were going over the sig fig things that I want to make sure that we're using proper significant figures here. So the first thing I need to do is the subtraction. So 101.5 minus 32. I am getting 69.5. And this is going to be degree C at the end. Oh, this is still degree F at this point. Let's just drop the units for now. But the question I have for you guys is, look at the number 32 there. How many sig figs are on that number? It's infinite, right? The thing is, that even though that's an exact number, you still have to apply the addition rule. Because or addition and subtraction rule, because you're still doing that operation. What I mean by that is that if you go up an order of magnitude or down an order of magnitude, you may gain or lose sig figs. We're still going by the number of decimal places. So if this one has 1 decimal place, our answer has 1 decimal place here. So we actually lost a sig fig with that. So look, we were at 4 sig figs initially. We're down to 3. All right, and then without clearing your calculator, multiply this by 5 over 9, and then we get 38.6. And the units on this would be degree C. If we were to end the calculation here, we would have 3 sig figs in our answer, because we then need to apply the multiplication rule. So then when you do that multiplication there, yes, the 5/9 is exact, but you have to apply the multiplication rule there as needed. The main thing that I see students do is they will forget to apply the addition subtraction rule here, and then they end up with one too many sig figs if the order of magnitude changed on the number. All right, and then how can I convert this to Kelvin? That was plus 273.15. That's basically taking into account the offset. So this is equal to 311 and 1 decimal place. So look how I gain a sig fig back, because I go by 1 decimal place because I was doing an addition there. All right, quickly, before we move on here, does anybody know the significance of 0 Kelvin? What's that?
The point at which all energy stops.
All motion stops. So the way that we define temperature in science is by the motion, molecular motion, and the absolute coldest possible temperature, or theoretically possible temperature, is where there's no motion at all. And from our current understanding of the way matter behaves, that is theoretically impossible, which works out for us mathematically because we're never going to have a temperature that low, so we don't have to worry about it. Oftentimes, especially when we get to the gas law chapter later on, we're going to have to convert everything to kelvins because of the fact you might have division by 0 or something. But for the most part, we're going to work with degree C in this class. All right. Do you guys want me to do more practice with you? Or are we good? We're good? Go ahead.
Can you explain why we only have 4 significant figures? 311.8.
For here?
Yeah.
All right, so first things first, just running through it real quick. So we had 1 decimal place in this portion because of the addition rule. And then multiplication rule gives us 3. And then when I went here, I did the addition rule again because I added 273.15 to it. So this was the number we were coming in with. It had 1 decimal place. So my answer has 1 decimal place. But because the order of magnitude changed, I ended up gaining a sig fig from it. Yeah, so be careful of that with the addition and subtraction rule. Sometimes you will gain and lose if the order of magnitude changes. So that's exactly what's happening here. All right, switch back to desktop. Okay, we do have a few more practices in here if you guys want to work them out. If not, don't. It's all up to you how much review you guys do. So the next thing I want to talk about here is some dimensional analysis. Let me just get all this stuff up here real quick. All right, so when setting up dimensional analysis, typically I like we have equivalency statements. They're basically your conversion factors. That's kind of like table information. The stuff that I would want you guys to be able to use or come up with on your own would be, for example, the first statement on there, that 10 to the 3 meters is 1 kilometer. You should be able to know that without having to look at a table. The lower one, though, where you have the 1 inch to 2.54, that's an English to metric conversion. I will provide that to you if it's needed. I don't plan on giving you a whole table, but if I think a conversion is needed, I'll put it in the question. And there might be times where I don't think a conversion is needed. I'll give it to you anyway to see if you use it or not. So be aware that sometimes when I post information in a question, you don't have to use it. And that's pretty normal for the textbook also and the online homework. So I do it also on the test. The main thing that I do when I'm setting up a conversion problem is a roadmap on how we get there. So I think the best way to explain this would be to go ahead and take a look at a problem. So let me switch back. All right. already ordered that one. So let's go ahead and say that we have something that is 10 kilometers or 10.5 kilometers. And I need to convert this to say inches. Okay, how many inches is that? So in the case where, and suppose that the only conversion factor that you were given would be 1 inch is 2.54 centimeter. Now, as I just said, I don't expect you guys to remember all these different conversions from English to metric, but some of them you might. This might be one because we see it so often. All right, so in order to use this conversion factor, I need to figure out first how to go from kilometer to centimeters because I can't use that conversion directly. So I'm going to think about that as a path. So I do know that we have kilometer, we can go to meters. And then from meters, we can go to centimeter. And then after we're at centimeters, we're good now, we can go to inches. As you have enough practice with this stuff, this part should be mental. Like you're doing this kind of analysis in your head, and then that tells you, okay, we need 3 conversion factors set up here. So we do know that there are this is km. So I want to go from kilometers to meters. There's a couple different ways you can do this, but I like to work with positive exponents. So to do that, I need to put something with the meter. So what should I put there? Yep, 10 to the third. I recommend if you're working around in metric to go ahead and write these in this notation. Don't write out 1,000 because you may see sometime that things might cancel out really easily, or you might be able to do some exponent tricks to get things to add up or to get the math to work out a little bit easier. I'm thinking about time-saving techniques because your exams in this class are long. So just a heads up, they're kind of long. All right, next conversion I need is to go from meters. So the given unit on the bottom, desired on top. You guys remember what that conversion is? And I like to work with positive exponents. 10 to the 2 with centimeter, right? Okay, before we move on this, I want to show you guys something. Didn't we have that table?